Welcome back. Let's learn about intersections and angles between lines and planes. Alright, so in the previous two lessons, we looked at how to represent lines and planes in 3D space. And so now that you are familiar with those concepts, we can take a look at how lines and planes can interact with each other in 3D space. In particular, we're going to look at their intersections and angles of intersection. All right, and so there's three different types of intersections that we're going to look at in this video. First, we're going to look at the intersection of lines and planes. Then we'll look at the intersection of two lines, and then we'll look at the intersection of two planes. And in addition to looking at how to find each of these types of intersections, we will also look at how to find the angle of intersection for each of these types. Okay, but with that, let's take a look at our first type of intersection. Okay, so here's our first type of intersection. We're going to be looking at the intersection of lines and planes. And this type of intersection is going to be a point. And you can see that with this diagram here. We have a plane P and a line L that are intersecting, and that intersection will be a point. Now, it is possible that the line could be within the plane. In that case, every single point along the line is contained within the plane. And so in that case, there really isn't an intersection because the line would just share all of its points with the plane. But other than that, if a plane and a line intersect, they will only intersect at one point. Okay? And so what we are interested in doing is being able to find that point of intersection given the equations of a plane and a line. And so here's how we're going to do that. The first step to finding that point of intersection is to plug the line into the plane. All right, and that sounds a little bit confusing, but what I mean by that is that you want to have the parametric equations of your line, where you have equations for x, y, and z, and you want to plug those three equations into the equation of the plane. And you'll see what I mean by that when we look at our example in just a second. But once you plug in those parametric equations of the line into the plane equation, what you want to do is then solve for that parameter t if possible. All right, if you can find a value for that parameter t, what you can then do is plug that value of t back into the parametric equations for the line, and that will give you the point of intersection. All right, now if for some reason the parameter t cancels out in that equation, meaning that it won't be possible to solve for that parameter, there's two different things that could happen. If you can't solve for t because it's canceled out, then you're either going to be left with a true statement for that equation, meaning you might have 1 is equal to 1 or 5 is equal to 5, something like that. If you have a true statement, then that means that the line is contained within the plane. Now, if you're left with a false statement, something like 2 equals 1 or 3 equals 4, right, things that aren't true, then what that means is that there's no intersection. The plane and the line do not intersect. Okay, and so those are the basic guidelines that you want to keep in mind, but let's actually take a look at an example where we find the point of intersection between a line and a plane. All right, so here's our example. We want to find the point or points of intersection, if any, of the plane and line. All right, and so we have the equation of a plane right here. We have 2x minus 2y plus z equals 12, and then we have parametric equations for a line in 3D space. We have x equals t plus 1/2, and then y equals negative t minus 3/2, and z equals 2t minus 1. Okay, now the first thing that you always want to do if you want to find the point of intersection between a plane and a line is plug in the parametric equations for that line into the plane. Okay, and so we have these three parametric equations for x, y, and z that represent this line. What we want to do is plug each of them in for x, y, and z in the plane equation. And then once we do that, we want to see if we can solve for the parameter of t. Okay, so let's do that. We're going to have 2 times t plus 1/2 minus 2 times negative t minus 3/2, and then we're adding that to 2t minus 1, and that's equal to 12. All right, and so now what we want to do is simplify this equation so that we might be able to solve for that parameter of t. So we're going to be multiplying 2 through this quantity, negative 2 through this quantity, and then just adding these two terms. So we'll have 2t plus 1 plus 2t plus 3 plus 2t minus 1, and that's equal to 12. All right, and so now we want to combine our like terms. We have 2t, 2t, and 2t. That will become 6t. So we have 6t, and then we have 1, 3, and negative 1. That positive 1 and negative 1 will cancel out. So we have 6t plus 3 equal to 12. Then if we subtract 3 from both sides of the equation, that will give us 6t is equal to 9. And then dividing both sides by 6 will give us that t is equal to 9/6, which reduces to 3/2. All right, so we were able to solve for t here. We found that t was equal to 3/2. And so what that means is that we do have a point of intersection between this plane and this line. But now in order to find that point of intersection, we have to plug this value of t back into the equation of the line, and that will give us an x, y, and z coordinate of that point of intersection. All right, so let's do that. Let's plug t equals 3/2 in for t in each of those parametric equations. So we'll have x equals 3/2 plus 1/2, then y equals negative t, or negative 3/2 minus 3/2, and then we'll have z equals 2 times t, or 2 times 3/2 minus 1. Now if we simplify, 3/2 plus 1/2 is 4/2, and 4/2 is the same as 2. Then for y, we have negative 3/2 minus 3/2, which will be negative 6/2, and that is the same as negative 3. And then for z, we have 2 times 3/2. Those 2's will cancel out, and so we'll have 3 minus 1, which is equal to 2. And so the point of intersection will have an x-coordinate of 2, a y-coordinate of negative 3, and a z-coordinate of 2. So the point of intersection is 2, negative 3, 2. That is the final answer to this problem. That is the point of intersection between this plane and this line. And it's important to note that it is the only point of intersection. All right, since we were able to solve for t in this equation, that value of t will give you the one point of intersection for that line and that plane. All right, and so that's it for this example. Now we're not going to look at another one in this video, but I want to briefly talk about what happens if you can't solve for t in this equation, right? Let's say that you plug in your parametric equations for your line into the plane equation, and then as you simplify, you get to a point where t cancels out. All right, now this doesn't actually happen in this example, but let's say that in this step right here, that we didn't have this 2t right here, and then this 2t was a negative, right? And so what would happen is that 2t and negative 2t would cancel out, and so the parameter t would be eliminated from the equation. We would be left with 3 equals 12, right? You would have 3 equals 12, which is not a true statement, and so you would say 3 is not equal to 12, and if that was your result, what you would then conclude is that the line and the plane do not intersect. Okay, but now what happens if this statement is true, right? Let's say that instead of having 3 equals 12, we end up with 12 equals 12, right? 12 equals 12 is a true statement. Once again, that's not what we actually get from this calculation. I'm just giving you a what-if scenario here. What if we get 12 equals 12 or some other true statement? Well, if you would get a true statement that checks out, then what that would mean is that the line is in the plane. In other words, every single point along the line is also contained within the plane. And so in that case, your final answer or your conclusion would be that the line is in the plane and all of the points on the line are shared with the plane. There's an infinite number of points of intersection. There's not just one like there was in this actual example right here. Okay, so those are the different scenarios that you might encounter. You might be able to solve for t and find one point of intersection, or you might get an untrue statement, meaning that the line and the plane don't intersect, or you will get a true statement, which tells you that the line is in the plane. Okay? And so that's it for our example on the intersection between a plane and a line. But now let's talk about how we find the angle of intersection between a plane and a line. All right, because if a plane and a line intersect at one point, then there will be an angle between that plane and that line. Okay, so now that you've seen how to find the intersection between a line and a plane, now what we want to do is look at how to find the angle between the line and the plane. And just like I kind of mentioned earlier, in order for us to be able to find an angle between a line and a plane, it is important that they actually intersect at just one point, right? If the line and the plane never intersect, then there won't be an angle between them. And if the line is in the plane, then the angle between them would be 0. All right, so there's no angle between them in that case either. And so the angle of intersection that we're interested in here only occurs when a line and a plane intersect at one point. Okay, and so this is what it looks like in a 3D view. But now if we look at a 2D side view, this is our plane from the side, and this is the line intersecting with the plane at one point. We want to find the angle between that plane and that line, this angle right here. And so the question is, how do we find that angle? Well, one thing that we're going to need to help us find that angle is a normal vector for this plane. All right, there's no other way for us to really relate a plane to a line without using the normal vector for that plane, because in order to represent a plane, we need a point in the plane and a vector perpendicular to it, or a normal vector. So a normal vector for a plane is a very important part for identifying that plane. So we're going to want to draw that in this diagram here. I'm going to draw it like this. That is going to be a normal vector to this plane. And so that would mean that this angle right here would be a right angle, or a 90-degree angle, because a normal vector is perpendicular to the plane. And so now that we've drawn that normal vector, how can we make use of it and the line in order to find that angle of intersection? Well, in order to find that angle, what we have to do is consider the angle between the normal vector and the line. All right, and that angle isn't actually the angle of intersection. The angle between the normal vector and the line would actually be this angle right here that I'm going to label with theta. This angle is actually the angle between two vectors, right? Because a normal vector is a vector, and then we can describe the direction of the line with a vector parallel to that line, the line's direction vector. Okay, that's what this angle theta is right here. It will be the angle between the normal vector of the plane and the direction vector of the line. And so we can find that angle because we have a formula that allows us to calculate the angle between two vectors, right? It looks like this. We know that cosine of that angle theta between the two vectors is equal to the dot product of the two vectors, which in this case is the normal vector, and then the direction vector from our line, which I'll represent with vector v, and then we divide that dot product by the magnitude of those two vectors. So we have the magnitude of the normal vector multiplied by the magnitude of the direction vector. Okay, this is the formula that we use to calculate the angle between two vectors. And now if you wanted to add one more thing to this equation, what you could do is put absolute value bars around the dot product. And what that will do is ensure that the angle that you find once you solve for theta by taking the inverse cosine of both sides of the equation, the absolute value bars will ensure that the angle you get is an acute angle. All right, in other words, you're going to get this smaller angle between the two vectors rather than the bigger angle or the obtuse angle that would be between the two vectors. All right, we want this smaller angle right here, the acute angle, not the bigger angle. And so I'm going to use those absolute value bars in this case. Okay, but now it's important to realize that this is not our final equation. All right, this will give us the angle between the normal vector and the line, but that's not the angle we want to find, right? We want to find the angle of intersection, this angle right here between the plane and the line. And so how would we use this angle to find that angle? Well, notice that the plane, its normal vector, and the line create a triangle, right? We have a triangle right here with 3 different angles. We already know that this angle right here is an angle of 90 degrees, and we know how to find this angle, that angle of theta. We can find it using this formula. And so what we can do to find the angle of intersection is subtract those two angles from the total amount of degrees, or the total measurement of the interior angles of a triangle, and that will give you that angle of intersection, that third angle that you don't know. And so remember, the angles of a triangle will add up to be 180 degrees. And so what we can do to find that angle of intersection is take 180 degrees, subtract that 90-degree angle, and then subtract theta. All right, but then we can simplify. 180 minus 90 is 90. And so the angle of intersection will just be equal to 90 degrees minus theta. And we can solve for theta in this equation by using the inverse cosine function on both sides. And so if we do that, here's what you'll find. The angle of intersection between a line and a plane will be equal to 90 degrees minus inverse cosine of the absolute value of the dot product between a normal vector of the plane and the direction vector of the line divided by their magnitudes. And so we can write that in right there. That expression represents theta. Okay? And so maybe you want to write this formula down. This is the formula for finding the angle of intersection between a line and a plane. And so let's go back to our example from earlier and see if we can find the angle of intersection. All right, so here's our example from earlier. We found this point of intersection between this line and this plane. And so since we know that this line and this plane intersect at just one point, we can find the angle of that intersection. And so let's see if we can find that angle of intersection. First thing that we need to do is identify the normal vector for our plane and the direction vector for our line. And those are going to be pretty easy. The normal vector of the plane will just be a vector with the components that are the coefficients of x, y, and z. So that will be 2, -2, and 1. All right, so we'll have 2, -2, and 1. And then the direction vector from our line, that will be a vector, vector v, with components that are the coefficients of the parameter t in each parametric equation. So the x component of the vector will be 1, the y component will be -1, and the z component will be +2. All right, so we have 1, -1, and 2. And so those are our two vectors that we can use to find the angle of intersection here. Remember what our formula looks like. To find the angle of intersection, we have to take 90 degrees minus inverse cosine of the absolute value of the dot product of those two vectors divided by their magnitudes. And so before we set this up, let's find the magnitude of each of those vectors. The magnitude of the normal vector will be equal to the square root of the sum of its components squared. Now 2 squared and -2 squared are both 4, and then 1 squared is 1. So we have 4 plus 4 plus 1. And 4 plus 4 is 8 plus 1 is 9. And so this just becomes the square root of 9, which is equal to 3. Now the magnitude of vector v will be equal to the square root of the sum of these components squared. And 1 and -1 squared are both 1, and 2 squared is 4. And so we have 1 plus 1 plus 4. And 1 plus 1 is 2 plus 4 is 6. So we have the square root of 6. All right? And so now we can set up this equation. This will be equal to 90 degrees minus inverse cosine of the absolute value of the dot product between the normal vector and the direction vector. So we're going to be taking the sum of the product of their corresponding components. So we'll have 2 times 1, which is 2. So we'll have 2 plus -1 times -2. That will be +2. So we have +2. And then we're adding 2 times 1, which is 2. Okay? And then in the denominator, we're multiplying the magnitudes by each other, so we'll have 3 times the square root of 6. All right, so I'll write 3 times the square root of 6. And now, if we simplify, 2 plus 2 plus 2 is 6, and the absolute value of 6 is 6. So really what we have here is just 6 divided by 3 square roots of 6. And I'm not going to bother to simplify that any further, because now what we can do is just take the inverse cosine of 6 divided by 3 square roots of 6. And what we will have is that this angle of intersection is equal to 90 degrees minus 35.26 degrees. And there are some more decimals there. I just rounded off to 2 decimal places. All right, that is the result of inverse cosine of this expression. And then if you subtract this angle from 90 degrees, you will find that the angle of intersection is 54.74 degrees. And once again, that is a rounded off value. Okay, and so 54.74 degrees is about the angle of intersection between this line and this plane. And so that's it for this type of intersection. You now know everything you need to know about the intersection of lines and planes. Now let's take a look at our second type of intersection, which is the intersection between two lines. Hey there, real quick, before we get to the next part of this lesson, if you find my tutorial videos here at JK Math to be helpful and you want access to more content such as exclusive bonus videos and dark mode versions of my videos, I'd invite you to check out my membership site, JK Math Plus, where all of that content is available. To learn how to join and see a full list of everything you'd get access to as a member, you can head over to jkmathematics.com/plus. I'll have a link for that in the description of this video. Okay, so if you're interested in becoming a member, feel free to check that out. It's a great way to support me and the tutorials I make, as well as a great way for you to learn math better. But for now, let's get back to the lesson. All right, so next up, we're going to take a look at the intersection of two lines in 3D space. And as you might have been able to guess, the intersection of two lines will be a point. And so you can see that with this diagram right here. We have line 1 and line 2 that intersect, and that intersection is, of course, a point. All right, but now before we take a look at how to find that point of intersection, it is important to realize that not all lines in 3D space will intersect. There's actually 3 different types of interactions or relationships between lines in 3D space. And I just want to briefly talk about what they are. In 3D space, lines can intersect at a point. They can be parallel, or they can be skew. All right, now if lines are parallel, what that means is that their direction vectors are parallel. In other words, the direction vectors for those two lines are scalar multiples. And so if you can show that the direction vectors of two lines are scalar multiples, then you can conclude that those two lines are parallel. But now if two lines are not parallel and they also do not intersect, which can happen in 3D space, unlike in 2 dimensions, then those lines are what we call skew. They are skew lines. And so those are the 3 different types of relationships that you can have between two lines in 3D space. But now keeping that in mind, let's talk about the general process of how we can find the point of intersection for two intersecting lines. And so there's 3 steps or 3 guidelines that we're going to follow here. The first step is to check if the lines are parallel. All right, and that's as simple as taking a look at the direction vector for each line and seeing if those direction vectors are scalar multiples. If they are, then the lines are parallel and they obviously won't intersect, and so that would be the end of your work. But if they're not scalar multiples, then the lines are not parallel, and so they could intersect, which brings us to the second step, which is if your lines are not parallel, you want to set the parametric equations equal from those lines. So the x equations, y equations, and z equations, you want to set those corresponding equations equal to each other and solve for the parameters using 2 equations. All right, so since we're going to have 2 different lines, each of those lines will have their own unique parameter. And we're going to want to solve for those parameters using 2 of the equations that we create. And then once we do that, that leads us to step 3, which is to check those parameters in the third equation that we didn't use. And if that results in a true statement, then your lines intersect, and you'll be able to find the coordinates of that point of intersection using those parameters. But if you end up with a false statement, then your lines do not intersect, and therefore are skew lines. All right, and so those are the 3 steps, or the 3 guidelines that we're going to follow. If you're not quite understanding the process yet, don't worry, because we're going to take a look at an example next. All right, so here's our example. We want to determine whether the lines intersect, and if so, find the point of intersection. All right, and so we're going to go through those 3 steps, or those 3 guidelines that we just looked at. And the first step was to determine if our lines are parallel, because if they are, then they don't intersect, and so we won't be able to find a point of intersection. Okay, and so what we have to do here is find a direction vector for each of these lines. And so let's start with line 1. Remember that when you're given a set of parametric equations for a line, that the components of a direction vector can be found by looking at the coefficients of the parameter. In this case, for line 1, our parameter is t1, and then of course for line 2, the parameter is t2. But let's focus on line 1 here. The direction vector for line 1 I will represent with vector v1. And that will have the components that are the coefficients of that parameter t1 from each equation. So the x component will be -1, the y component will be -2, and the z component will be 1. So we'll have -1, -2, and then 1. And then for line 2, I'll represent a direction vector for that line with vector v2. And that vector will have the components of the coefficients of t2, that parameter, from each of those parametric equations. So we'll have 3, 2, and 1. All right, so I'll write 3, 2, 1. And so those are the 2 direction vectors that come from these 2 lines. Now what we want to do is determine if they are parallel or not. In other words, are they scalar multiples? And just by looking at them right away, we can definitely tell that they are not scalar multiples, right? We don't even have to look at the numbers. If you just look at the signs of those numbers, for vector v1, two of them are negative, but the last one is positive. But then for vector v2, all three components are positive, so it's going to be impossible for you to pull out a scalar multiple or a scalar value out of each of those components such that the signs match up. Okay, so it's going to be impossible for us to show that these two vectors are scalar multiples, which means that our two lines are not parallel. Okay, we can say that for sure. They could intersect, but we don't know that. They could also be skew, and so our next step is now to determine if they intersect. And we don't need the direction vectors anymore to do that, so I'm going to erase those. But now we're on to the second step of our process here. What we now want to do to determine if these two lines intersect is set their parametric equations equal to each other. We're going to create a system of equations involving three equations. All right, we're going to set the x equations equal to each other, the y equations equal to each other, and the z equations equal to each other. And the reason we do that is because if you think about what these parametric equations represent, what they do is they give you an x, y, and z coordinate of a point on that line given a particular value of that parameter t1 or t2. And so if each of those parametric equations represents a coordinate of a point, then what we're doing by setting those parametric equations equal to each other is finding any shared points between those two lines. In other words, a point that is on both of those lines, which is where those lines would intersect. Okay, so that's what we're doing here. And so let's actually set these equations equal to each other. I'll start with the x equations. We're going to have 1 minus t1 is equal to 2 plus 3 t2. All right, we made that equation by setting this equal to this. Now let's work on our y equation. We'll have 3 minus 2 times t1, and that will be equal to 3 plus 2 times t2. All right, we set this expression equal to this expression. And then finally, our z equation, we will have t1 equal to 1 plus t2. And so I'll write that down. We have t1 equal to 1 plus t2. Okay, and so now what we have here is a system of equations and then two variables that we need to solve for in that system. And so we need to figure out what the value of t1 and t2 is. Now you can choose to go about this however you like. However you like to solve systems of equations is fine. You can use the method of elimination from algebra, or you can do what I'm going to do here, which is the substitution method. But before you use any of those methods, what you want to do is just pick two equations to work with. All right, and then the third equation that you don't use is going to be the equation that you use to check and see if your lines intersect. All right, and we'll talk about that more when we get there, but the first thing that you want to do here is just pick two of these equations to work with. Now, as I mentioned earlier, I'm going to use the method of substitution, and so I like this last equation right here because it already has that t1 is equal to some other expression, and so I'm going to choose to use this equation, and then I'm going to use this one up here. Okay, so I'm going to use the x equation and the z equation. I know that t1 is equal to 1 plus t2, so what I'm going to do is plug that value in for t1 in this equation and then solve for t2. All right, so I'm going to have 1 minus t1, which is 1 plus t2. So I'll write 1 minus 1 plus t2. Remember that you are subtracting t1, and t1 is composed of two terms, so you need to subtract both of them. That's why I have parentheses around them. And then that will be equal to 2 plus 3 times t2. Okay, so now let's simplify. We'll have 1 minus t2 is equal to 2 plus 3 times t2. And then 1 minus 1 is 0. So those two values cancel out. And so we have negative t2 is equal to 2 plus 3 times t2. If I subtract 3t2 from both sides of the equation, that will give me negative 4 t2 is equal to 2. And then to solve for t2, we can divide both sides by negative 4, and that will give us that t2 is equal to negative 1/2. And so that's our value of t2, and now this is the part where you want to be careful. Remember what two equations you used, because then what you want to do to get the other parameter, t1, is plug that value of t2 into one of those two equations that you used. All right, don't use the third equation yet. We will use that in just a little bit. For now, we just want to find the value of t1 that corresponds to this value of t2 when using these two equations. All right, and so this equation right here is pretty easy to work with. we have that t1 is equal to 1 plus t2, and so we'd have t1 is equal to 1 plus negative 1/2, right? We'll have t1 is equal to 1 plus negative 1/2, which gives us t1 is equal to positive 1/2. And so now, from these two equations that we chose, we found that t1 is equal to 1/2 and t2 is equal to negative 1/2, which are the two values of those two parameters where the x and z coordinates are the same for these two lines. Now the question is, if we plug these two values into that third unused equation, the equation for y, will we get a true statement? If we do, then we can conclude that these two lines intersect at a point. If they don't, then the lines will be skew. All right, and so let's check this here. We found from these two equations that t1 is 1/2 and t2 is negative 1/2, but let's see what happens if we plug those values into this third equation that we didn't use. And so let's perform that check here. We're going to have 3 minus 2 times t1, which is 1/2, so we're multiplying by 1/2, and then that will be equal to 3 plus 2 times t2, which is negative 1/2. All right, now let's simplify. 2 times 1/2 is 1. So we have 3 minus 1 equal to 3 plus 2 times negative 1/2, which will be negative 1. So really we have 3 plus negative 1, which is 3 minus 1. And so now we have 3 minus 1 on both sides, which becomes 2. And so what we'll have here is 2 equal to 2. And that is a true statement. 2 is equal to 2. It's the same value. And so because that is a true statement, we can conclude that these two lines do intersect, okay? If instead we got something like 2 equals 1 or 2 equals negative 7, then the statement would be false, and we would be able to conclude that the lines do not intersect and therefore are skew, okay? But now, let's actually find the point of intersection, and this part's pretty simple. In fact, we already found the y-coordinate of our point of intersection. It's 2. It's the y value you get when plugging in one of these parameters into their corresponding y equation from these parametric equations. And so if we want to find the x and z coordinates, we could just plug either t1 or t2 into their corresponding equations for x and z from either line. And I'll do that, but if you're ever not confident in those two values of t1 and t2 that you found, what you could do is just plug both of them into each of these equations right here and see if those statements are also true. And whatever you find on either side of the equation will be your x and z coordinate. All right, and so I'm going to do that. Let me show you it that way. I'll do the x coordinate right here. We have 1 minus t1, so we'll have 1 minus 1/2. So I'll write 1 minus 1/2, and that will be equal to 2 plus 3 times t2. And t2 is negative 1/2. So we have 2 plus 3 times negative 1/2. 1 minus 1/2 is 1/2. So we have 1/2 is equal to 2 plus 3 times negative 1/2. 3 times negative 1/2 is negative 3/2. And then if you add 2 to that, 2 is the same as 4/2. So we have 4/2 plus negative 3/2. That will give us positive 1/2. And so both sides of the equation are equal, which means that our x-coordinate is 1/2. And then finally, for the z-coordinate, we have t1 equals 1 plus t2, and so t1 is 1/2 and t2 is negative 1/2, so we have 1/2 is equal to 1 plus negative 1/2, and of course 1 plus negative 1/2 is 1/2, and so that checks out. We have 1/2 equals 1/2. And so now we have the x, y, and z coordinates for the point of intersection between these two lines. The point is 1/2 to 1/2. All right, that is the final answer to this example. Okay, and so that's how you find the point of intersection between two lines. But now how do we find the angle of intersection between two lines? All right, well, if you want to find the angle of intersection between two lines that you do know intersect at some point, finding that angle of intersection is pretty straightforward. It's not going to be as complicated as finding the angle between a line and a plane, because we don't have to work with any normal vectors here. Instead, if we want to know the angle between these two lines, we just have to determine the angle between their direction vectors. And we have a formula that allows us to find the angle between two vectors. And so if we can find the angle between the two vectors for these two lines, then that will be the angle between the two lines. All right, and so that formula will look like this. We'll have cosine of theta, the angle of intersection that we want to find. That would be this angle right here. That would be angle theta. cosine of that angle will be equal to the dot product of the two direction vectors from those lines. And so I'll say that the direction vector of line 1 is vector v1, and the direction vector for line 2 is vector v2, and that will be divided by their magnitudes multiplied together. So we'll have the magnitude of vector v1 multiplied by the magnitude of vector v2. Okay? And then you might also want to add these absolute value bars up top, because that will ensure that you get the acute angle between those two vectors and not the obtuse angle. All right, you want the smaller angle that is less than 90 degrees. Okay, and so it's not any more complicated than that. If you want to find the angle of intersection between two intersecting lines, you just use the formula for the angle between two vectors, where the two vectors in that formula are the direction vectors for those two lines. Okay, and so if we go back to our example from earlier, this was our example for determining if two lines intersected and finding that point of intersection. And we were able to do that, so we know that these two lines intersect. And so we can also find the angle of intersection for these two lines. And so that's what we're going to do now. And the first thing that we need to do is find those direction vectors again. We found them earlier when we determined if these two lines were parallel or not, but then I erased them because we didn't need them to find the intersection of the lines. But now we need them again for the angle of intersection. So let's write down those direction vectors again. The direction vector for line 1 will have components that are the coefficients of the parameter t1 in each equation. So we have -1, -2, and +1. So we'll have -1, -2, and +1. And then the direction vector for line 2 will have the components that are the coefficients of the parameter t2. So we have 3, 2, and 1. So I'll write 3, 2, and 1. And now, to find the angle of intersection, we'll have cosine of that angle is equal to the absolute value of the dot product of these two vectors. So we're going to be taking the sum of corresponding components. So we'll have -1 times 3, which is -3. Then we'll add that to -2 times 2, which is -4. And then we'll add that to 1 times 1, which is 1. All right, and then in the denominator, we need to multiply the magnitudes of these vectors together. We're going to have the magnitude of vector v1 multiplied by the magnitude of vector v2. And the magnitude of a vector is the square root of the sum of its components squared. So for vector v1, -1 squared is 1, -2 squared is 4, and 1 squared is 1. So we have 1 plus 4 plus 1. And then for vector v2, 3 squared is 9, 2 squared is 4, 1 squared is 1. So we have 9 plus 4 plus 1. And then 1 plus 4 plus 1 is 6, and 9 plus 4 plus 1 is 14. So we have cosine of theta is equal, and then in the denominator of that expression, we have the square root of 6 multiplied by the square root of 14. And then in the numerator, we have -3 plus -4, that's -7, plus 1 will be -6, but the absolute value of -6 will be +6. And so now, if we solve for theta by using the inverse cosine function on both sides of the equation, that will give us that theta is equal to 49.11 degrees. And I did round that off to 2 decimal places. There are more decimals there, but I decided to stop after 2 decimals. Okay? And so that is the angle of intersection between these two lines. And so with that, we're ready to look at our last type of intersection for this video, which is the intersection of two planes. All right, so for our last type of intersection, we're going to do things a little bit in reverse here. We're going to start by talking about the angle between two planes before we look at how to find the intersection of two planes. All right, and so in order to understand how to find the angle between two planes, we're going to analyze what happens when we have parallel planes and when we have perpendicular planes. All right, and so let's start with parallel planes. When two planes are parallel, they will have parallel normal vectors. All right, and so if you take a look at these two planes right here, plane 1 and plane 2 are parallel planes. And so if we were to draw a normal vector for each of those planes, which by the way, a normal vector is a vector perpendicular to the plane. So a normal vector for plane 1 might look like this, and then a normal vector for plane 2 might look something like this. All right, and so just like those two planes are parallel to each other, since their normal vectors have to be perpendicular to those planes, then those two normal vectors will be parallel as well. The normal vectors of parallel planes are scalar multiples. Okay, and in either case, whether you're looking at the parallel planes or their parallel normal vectors, the angle between the planes or the angle between the normal vectors will be an angle of 0 degrees or 0 radians, or an angle of 180 degrees or pi radians. Okay, if you have any angle that isn't those angles right there, then your normal vectors or your planes would no longer be parallel. Those are the only possible angles that you could have. Now for perpendicular planes, what we know about those planes is that they will have perpendicular normal vectors. And so here we have two planes that intersect at a right angle. The angle between them is an angle of 90 degrees, or pi divided by 2 radians. If we were to look at the normal vectors of these planes, we would see that they are also perpendicular, that they also have an angle of 90 degrees, or pi divided by 2 radians between them. All right, so a normal vector for plane 1 might look something like this. That could be that normal vector. And a normal vector for plane 2 might look something like this. All right, that would be that normal vector. It doesn't matter in each case where you draw those normal vectors. As long as they are perpendicular to their corresponding plane, you will notice that those two normal vectors are perpendicular, just like their respective planes are. And so the reason that I show you this, the reason that I'm showing you what parallel planes and perpendicular planes look like along with their normal vectors, is to show you that the angle between the normal vectors of two planes is the same as the angle between the planes, right? The angle between these two planes is 0 or 180 degrees, and that would also be the angle between two normal vectors for those planes. And then for perpendicular planes, the angle between them is 90 degrees, as is the angle between their normal vectors. Okay, and so since the angle between two planes will be the same as the angle between their normal vectors, we can find the angle of intersection between any two planes by finding the angle between their normal vectors. Okay, and we can find the angle between two normal vectors for two planes using our formula for finding the angle between two vectors. All right, so here we have two planes that intersect, and there's an angle between those two planes that we want to find. And so in order to find that angle, what we have to do is look at the normal vectors of those planes. And so this might be the normal vector for plane 1. So that would be the normal vector n1. And then this might be the normal vector for plane 2. And so that would be vector n2. And so using those two normal vectors, we can write the following formula for finding the angle between two vectors. We'll have cosine of that angle theta. That will represent the angle between the normal vectors, which is the same angle that will be between the planes, and that will be equal to the dot product of those two normal vectors. So we'll have vector n1 dot vector n2, and then we divide by their magnitudes multiplied by each other. So we'll have the magnitude of vector n1 multiplied by the magnitude of vector n2. Okay? And then just like with our other equations for finding the angle of intersection, I'm going to add in these absolute value bars to ensure that the angle that we find here is an acute angle, the smaller angle between those two vectors or those two planes. Okay? And so finding the angle between two planes is really that simple. You just want to find the angle between their normal vectors. And so that's how we find the angle between two planes. But now let's talk about how we find the intersection between two planes. Unlike the intersection between a line and a plane, or the intersection between two lines, the intersection of two planes will be a line, not a point. All right, and you can see that with this diagram right here. We have plane 1 and plane 2 that intersect, and their intersection creates a line. And so unlike our previous two types of intersections in the 3D coordinate system, we're not going to be looking for a point of intersection. We are looking for a line of intersection. And so the way we find that intersection is going to be a little bit different. And so let's go through the steps on how we find that line. The first step, just like with the intersection of two lines, is to check if the planes are parallel. All right, because if the planes are parallel, then they don't intersect, and so therefore there is no line of intersection. Okay, and so remember, we talked about this just a little bit ago. Two planes are parallel if their normal vectors are parallel. So you would just find the normal vector from the equation of each plane and see if those normal vectors are scalar multiples of each other. Okay, and so if you determine that the two planes are parallel, then they won't intersect, but if you find that they're not parallel, then they will intersect, and so you will be able to find a line of intersection. And so that leads us to step 2, which is if the planes are not parallel, you want to find a direction vector of that line of intersection by taking the cross product of the normal vectors. All right, and so let me explain why that works, because that seems really random at first. Why are we using a cross product of the normal vectors of these planes? And so let me explain what's going on here. If we want to find this line of intersection, what we're going to have to end up doing is creating either a symmetric equation or a set of parametric equations to represent that line in 3D. And so remember what two things you need in order to find a line in 3D. You need a point on that line, and you need a direction vector, a vector that is parallel to that line. And that direction vector is what this second step is helping us find. We are finding a direction vector for this line, a line parallel to that line of intersection, by taking the cross product of the normal vectors from our planes. And so if I draw in those normal vectors, this could be a normal vector for plane 1, so I'll represent that with vector n1. And this could be a normal vector for plane 2, so I'll write vector n2. And so if we're taking the cross product of those two normal vectors from those planes, how will that give us a direction vector for this line? Well, remember what taking the cross product of two vectors does. If you take the cross product of two vectors, what you get is another vector for one thing. You get another vector, not a scalar value or anything. You get another vector, and that vector that you get will be perpendicular to the two vectors involved in that cross product. And so if you take the cross product of these two normal vectors, what you're going to get is a vector that's perpendicular to those two normal vectors, and that perpendicular vector will either look something like this or like this, which will be a vector parallel to that line of intersection. All right, that line of intersection will be perpendicular to both of those normal vectors, and so we can find a direction vector or a vector parallel to it by taking the cross product of the normal vectors from those planes, okay? And so that's how we find the direction vector for that line, but then we also need a point on that line, which takes us to step 3, which is to find a point on the line and create an equation of the line using that point and the direction vector. And we'll talk about how to find that point on the line as we go through our example problem, which is what we're going to look at next. All right, so here's our example problem. This is also the last example for this video. We want to determine whether the planes intersect, and if so, find the line and angle of intersection. Okay, and so we have two planes here, plane 1 and plane 2. Plane 1 is x minus 2y plus z equals 0, and plane 2 is 2x plus 3y minus 2z equals 0. And so the first thing that we want to do here to determine if these planes intersect is see if they're parallel. Because if they are parallel, then they don't intersect, and there's no line of intersection. Okay, so we need to find a normal vector for each of these two planes. And so remember how you find a normal vector. A normal vector for each plane will be a vector with components that are the coefficients of x, y, and z from the equation of that plane. So the normal vector for plane 1 will have components of 1, -2, and 1. And then a normal vector for plane 2 will have components of 2, 3, and -2. Okay, and so now that we have those two normal vectors, can we determine if they are parallel? All right, because if the normal vectors of two planes are parallel, then the two planes are also parallel. And just by looking at these two normal vectors, we can conclude pretty quickly that they're not parallel, or in other words, that they're not scalar multiples, right? Because the signs of the components don't match up. For this normal vector, the components are positive, negative, positive, but for this normal vector, we have positive, positive, negative. So if we pull out a positive value out of all of the components in either of these vectors, none of those signs will change, and so they still won't match up. And if we pull out a negative scalar value out of each of the components in these vectors, then the signs will reverse, and they still won't match up. You'll have negative, positive, negative, and then negative, negative, positive. So that's not good. It's impossible for these two vectors to be scalar multiples. Okay, and if you have a hard time determining that, if you're really not sure if these two vectors are scalar multiples or not, don't worry about that step, because in the next step, in order to find the direction vector for the line of intersection, what you're going to be doing is taking the cross product of these two normal vectors, and if you find that the cross product is 0, then you know that those two vectors are parallel. All right, when you take the cross product of two vectors and you get 0, that means that the vectors are parallel. And so if that were to happen to you, then you would know that you made a mistake and those two vectors were actually scalar multiples. Okay, but with that, we did conclude that these two vectors are not parallel, and so therefore these two planes are not parallel, so they will intersect and will have a line and angle of intersection that we can find. Okay, and so the next thing that we want to do is take the cross product of these two normal vectors, and that will give us a vector perpendicular to both of those vectors, which will be the direction vector for the line of intersection. All right, and so I'm going to represent that direction vector with vector v, and so vector v will be equal to the cross product of vector n1 and vector n2. And so let's set up our cross product calculation. We're going to be setting up a 3x3 matrix and then calculating the determinant of that matrix. The first row will be the standard unit vectors I, j, and k. The second row will be the components of vector n1, and the third row will be the components of vector n2. So we'll just copy these components into this matrix. We'll have 1, -2, 1, and then 2, 3, -2. Okay? And so let's calculate the 3x3 determinant here. We'll start by looking at vector I. We're going to cross out the row and the column that it's in and use the remaining 4 values to calculate a 2x2 determinant. So we'll have -2 times -2, which is +4, minus 1 times 3, which is 3. So we have 4 minus 3 times I, and we will subtract the second term multiplied by j, and then add the last term multiplied by k. So now let's look at j in our matrix. We'll cross out the row and the column that j is in and use the remaining 4 values to calculate another 2x2 determinant. We'll have 1 times -2, which is -2, minus 1 times 2, which is 2. So we have -2 minus 2. And then finally, we're going to look at k. We'll cross out this row and this column and work with these 4 values. We'll have 1 times 3, which is 3, minus -2 times 2, which is -4. So we have 3 minus -4. Now, if we simplify, this will be equal to I plus 4j plus 7k. All right, 4 minus 3 is 1. 1 times I is I. -2 minus 2 is -4, but we're subtracting that term, so we have plus 4j, and then 3 minus -4 is the same as 3 plus 4, so we have 7k. All right, now this right here, that is the direction vector, vector v, for the line of intersection between these two planes. So we have one of the two things that we need to create a set of parametric equations that represent the line of intersection. The only other thing that we need now is a point. And so this is where things get a little bit tricky. In order to find a point on the line of intersection, what we have to do is recognize that these two plane equations would be a system of equations where the solution is the line of intersection, right? Remember in algebra, when you had a system of equations working with two-dimensional lines, that the solution to those systems of equations was always a point, the point of intersection between the two lines. In the same way, we have two plane equations that create a system where the solution is a line, the line of intersection between those two planes. So what we can do is find a point on that line of intersection by setting one of the variables in both equations equal to 0, and then solving for the other two variables in the resulting system of equations. All right, that will give you a point on that line. And so let me show you what I mean. What I'm going to do is set y equal to 0 in both of these equations. Now, you could choose to set x or z equal to 0 if you wanted to. It doesn't matter. After doing that, you would solve for the other two variables, and you would still get a point on the line of intersection, and you'd be able to create a set of parametric equations for that line. It doesn't really matter what you set equal to 0. Just pick one of the variables, and I'm picking y. And so if y is equal to 0, those two terms will disappear from these equations. So we will be left with x plus z equals 0, and 2x minus 2z equals 0. All right, and so now what we want to do is solve this system right here for x and z, and that will give us the x and z coordinates along with the y coordinate of 0 that make up a point on the line of intersection, or a point on that line that is the solution of these two plane equations. Okay, and so let's solve for x and z here. I'm going to use the method of substitution. So I'm going to solve for x and then substitute that in to this equation. If we subtract z from both sides, we can find that x equals negative z. And so substituting negative z in for x in this equation will give us 2 times negative z minus 2z equals 0. And so we'll have 2 times negative z, which is negative 2z, minus 2z, and that will be negative 4z equals 0. And so then dividing both sides by negative 4 will give you that z equals 0. And so since z equals 0 and x equals negative z, then x just equals 0. And so what we find here is that the x, y, and z coordinates of a point on the line of intersection between these two planes would be the origin, which is a pretty nice point, 0, 0, 0. All right, so a point on our line will be 0, 0, 0, the origin, and we can use that point along with this direction vector that we found to create a set of parametric equations that represent the line of intersection between these two planes. Okay, and so remember, a set of parametric equations for a line look like this. You'll have x equal to a times t plus x1, and then y equals b times t plus y1, and then you'll have z equals c times t plus z1, where a, b, and c are the direction numbers or the components of the direction vector. So that will be 1, 4, and 7. And then of course x1, y1, and z1 are the coordinates of the point on the line, which in this case is just the origin. So we don't even need to write those values in, they're all 0. So we will have x equals 1, that's our value of a, 1 times t. So we have x equals t, then y equals 4 times t, that's the value of b, the coefficient of j. So we have y equals 4t, and then z equals 7t. All right, c is equal to 7 because 7 is the z component or the coefficient of k. So we have z equals 7t, and that right there is a set of parametric equations that represent the line of intersection for these two planes. Okay, x equals t, y equals 4t, and z equals 7t. And so now we're almost done with this example. One more thing that we want to find is the angle of intersection here, which, as we discussed earlier, the angle between two planes is the same as the angle between their normal vectors. So we just have to find the angle between these two normal vectors. All right, so let's do that yet. Let's set up the formula for finding the angle between these two vectors. We're going to have cosine of the angle, which is theta, is equal to the absolute value of the dot product between these two normal vectors. So we will be taking the sum of the product of corresponding components. So we'll have 1 times 2, which is 2, plus negative 2 times 3, which is negative 6. And then we'll add that to negative 2 times 1, which is negative 2. And then we are dividing by the magnitudes of those vectors multiplied by each other. All right, and I'm just going to write that right into the equation here. We're going to have the magnitude of vector n1 times the magnitude of vector n2, and the magnitude of any vector is the square root of the sum of its components squared. So for vector n1, we'll have 1 squared plus a negative 2 squared plus 1 squared, so that will be 1 plus 4 plus 1. So I'll write 1 plus 4 plus 1, and then for vector n2, we'll have 2 squared plus 3 squared plus a negative 2 squared, which will be 4 plus 9 plus 4. So we have 4 plus 9 plus 4. Okay, now if we simplify, 2 plus negative 6 is negative 4 plus negative 2 takes us back to negative 6, but then the absolute value of negative 6 is positive 6. So we have cosine of theta equals 6 divided by the square root of 1 plus 4 plus 1, which is 6. So we have the square root of 6 times the square root of 4 plus 9 plus 4, which is 17. So we have the square root of 6 times the square root of 17, and I'm not going to bother to simplify that because we're just going to be putting it inside of the inverse cosine function in order to solve for theta. And so if we do that, you take the inverse cosine of both sides of this equation, you will find that the angle between the two planes is 53.55 degrees. And of course, I did round that off to 2 decimal places. Okay, but that's the angle of intersection between our planes. And so with that, that's it for this example. That's how you find the angle and line of intersection between two planes. And that was the last type of intersection that I wanted to look at in this lesson. But if you want to see some more examples, feel free to check out my examples video that I'll have linked here on the screen. If you have any questions, feel free to leave those in the comments But if you don't have any questions, this is all I had for now, so I will see you next time.